Hi, everyone. Welcome to today's webinar on better understanding RoadEng. My name is Erin, resident webinar host here at Softree, and I have to say this is probably one of my favorite webinars. You know, we have a set that we occasionally bring back every now and then, and better understanding RoadEng really, to me, is one of those essential webinars that I think every RoadEng user should check out. So first off, thank you for joining us here today. We are going to step into the webinar for the next 45 minutes and break down sort of the foundational modeling concepts behind RoadEng's powerful design engine. So whether you're new to the software or a seasoned user looking to just sharpen your understanding, this webinar, again, one of my favorites, and we hope you pick up some great information that's going to help guide you in your design process, as well as in some of the engineering decisions that you might need to make. So today, core concepts, there's essentially sort of 4 or 5 key building blocks and areas that we're gonna focus on. Really starting with the terrain model requirements, understanding how your tin surface is built, what affects its resolution, how that is going to impact your design. From there, we'll talk about the centerline and cross-section based model. So we're going to learn how RoadEng's dynamic templates are adapting to the terrain, to different material conditions, and the role of the centerline in that model. And then probably, I'm going to say, the most important topic of the day, report points. Why these are the backbone of the volume calculations that we're going to do in RoadEng, some tips to use them effectively without slowing down your project, as well as we're going to discuss a couple situations where you're going to want to add additional report points to help improve your modeling. And from there, we're going to talk about several volume-related topics, including how volume calculations are done with the average end area model, discuss the basics of the mass haul, and touch a little bit on expansion and compaction factors. So, just get us started, add a little bit of context. And this is really for folks that are not quite as familiar with the software. We're going to start off with a quick 3-minute mini demo. It's a recorded video. Wish me some luck and keeping pace with it, because it's going to go fast. But hopefully it gives you a good sense of what the software does and really sets the tone for a lot of these key topics that we're going to discuss here today. So our software, if you don't know it, it is modular. So we're going to start off here in the terrain module. And the terrain module is really our space for working with your topo surface. So in this example, importing 4 different LiDAR tiles. They come in initially just as points. We need to convert those points in our first step into what we call an original ground or tin surface, and we use the generate tin dialog for that. So once you've imported your points, turned it into a tin model, don't worry, we're going to discuss that part in more detail. We save the file, and then that is going to be the basis of our project in the location module. So that's the second module. So in the location module, we begin by clicking new project. Don't press open, although it feels like you should. And here we're going to link it to that original ground file that we created, that terrain file. Now, normally I would, and if I was doing a demo, the first thing I would do is I'd configure my cross section. But when you're trying to design a road in 3 minutes, we don't have time for that. So we're going to roll with the default typical cross section. And then we can start by clicking in an alignment. So RoadEng, really dynamic window-based updating tool. What's happening in our plan window is having an impact in all of our other windows. So as we click in this alignment, even as we add horizontal curves to it, the impact of those changes is going to be reflected in all the other windows. So here we're doing some manual design, but of course, if you checked out any of our other webinars, we of course love our optimization tools, and we can leverage those to create that initial horizontal alignment. We can do that with Path Explorer. And then as we move into the profile editing, that we have the opportunity as well to use an optimization tool there. So profile editing, if you can see it, our cursor's in the far left window, adding in a profile. Our grades are getting displayed as we do it. And everything that we can do in all the windows is very much adjustable. So as you adjust your profile window, your 3D view, your volumes, your cross sections, it's all updating in real time. And we're going to spend a lot of today's webinar talking about just those things: volumes, cross sections, really, really important concepts. So here we've done our vertical profile in this quick 3-minute design. We can add vertical curves as well to it. So here we can set our K value, implement some curves. And again, as we make those changes, everything updates. And that's really the kind of, core essence of RoadEng. It's a very dynamic, real-time updating interactive design tool. Now, you can iterate, fine-tune, material balancing. Again, we're going to talk a little bit about material balancing in today's webinar. And then from here, we'd sort of look at output for either, communicating your design, construction, adding culverts. But really, core essence of what we showed you, again, very dynamic, and it's really all based on the core topics that we're going to talk about today. And so this little 3-minute mini demo started off in the terrain module, and it started off by creating or importing some topo data and then creating a tin surface. So that's really our first concept. I should say, in terms of how we're going to do this webinar. Don't worry, it's not me talking the whole time. Our resident webinar main presenter is with us, training manager Matt. He is here. I'm going to introduce a concept. We'll talk about a little bit about it with some slides, pass it to Matt. We'll jump in the software. Okay, first concept, tin surface. So we obviously cannot design a road floating in the air. We really need to understand what the original ground surface looks like. And this original ground surface could come from a variety of different survey formats, such as total station survey. So we've got a conventional one shown up here on the screen. It could come from LiDAR, it could come from DEM, drone data, GPS, pretty much any standard format that includes elevation. Now, these are our survey points, and right now this is just the data imported and we don't have a surface. So as you saw in that 3-minute mini demo, we pressed the terrain calculation, generate tin dialog. And what that does is that generates a triangular irregular network. That's what tin stands for. And that's what's shown here on the screen. And that really connects all our points and allows us to generate a 3-dimensional surface. Now we can use things, especially in conventional data, like break lines to change a little bit of how this surface looks. But the idea that there are triangles connecting all of our survey points holds true no matter what surface you are working with. And that includes when we work with things like LiDAR data or DEM data. Now, a really big important note, not all tin surfaces are the same resolution or the same accuracy. And as you can see here in the 3 images on the screen, take, for example, the one on the far left, this is low resolution SRTM data. And on the far right, pretty much the complete opposite, we've got much higher resolution LiDAR data. Now, the vertical and horizontal density of the points and their accuracy is going to give us the quality of the tin surface. So if you had the option between the 3 choices, obviously the higher resolution the data, the more dense it is, the higher quality it is. And really, RoadEng is going to ingest all of these different tin surfaces or topo data and create tin surfaces from them. And what you choose to work with is really one of those engineering decisions that we encourage you to consider. So when if you're designing a road, or any type of corridor, I should say, being aware of the resolution of your data, because what you put in is essentially a very, very key factor in the accuracy of your road design. So that's a little bit about resolution, and then a really fun one, and this one's coming up all the time right now, as we're seeing clients work more and more with contour data. And so contour data is really interesting because once upon a time there were a point cloud essentially, and that data was then interpolated into contours. And now we're rebuilding a surface from contours. And I feel like the picture on the right shows it really, really well here. We've lost a lot of that original data that's happening between the contour lines. So as you have contours with higher gaps between them, or larger distances, I should say, you're going to lose more and more data. So whenever possible, if you have the ability to access it, getting that original data that was used to generate the contours is Yes, highly recommended. Okay, that's my quick public service announcement. I am going to pass it now over to Matt. Enough for me. Let's go take a look at our first core concept to help you better understand RoadEng, and that's really all about terrain modeling. So Matt.
All right.
I'm attempting to make you the presenter.
All right. Cool. So as the workflow that Aaron showed goes, we're going to start in terrain. And yeah, of course, for this webinar, I'm not going to just run through a workflow, but we're going to start in terrain as we talk about these really important concepts that we build on for everything else. So opening up terrain, we are going to click insert, and I am going to bring in some conventional survey data. So this conventional survey data, just as a little bit of a sneak peek here, of course, we've got point number, coordinate, elevation, and point code. So when we bring that in, we can use an IOP. It can connect the dots for us. And well, we bring that in and voila. Now for this, I'm gonna click my 3D view as well. So we can see both of these views. And so that information, it's 3D information. We have a combination of points and lines. We can take that and we can turn it into a surface. Now with this, I'll zoom in a little bit here and well, you may be able to see, as Aaron introduced, we have a series of triangles making up this surface. So that is our tin surface. And well, if we want to see what that actually looks like in the plan view, we can see how those triangles are being interpolated from one side to the other. Now with conventional survey data, when we bring that in, it's fairly sparse. So if we look here, we're not really relying on, well, the density of the points to give us this really good representation of what we're dealing with. We can see here we have points that are almost 20 meters apart. But these points and lines, they're explicitly chosen by the surveyor. And well, we can do things like add break lines out of them. And those really control how the triangles are defined. Now, dealing with conventional survey data versus LiDAR or DEM data can be quite different. And for this, if we pop open another instance of terrain, and we come in here, I'm going to grab my LiDAR tiles. So these are the last tiles. We can bring these in. Now, last data is classified, so I want to just bring in my ground points. We'll hit OK. We'll hit OK. We'll zoom in here. We can see that, well, we've got an awful lot of points. We've actually got, well, about 2.6 million points in this example. We're going to model our surface. And in this case, we don't have to worry about break lines and connect the dots. Since that data is so dense, we get really small triangles to, well, define and show how things are shaped. Now, if we take both of these and we look at one on one side and the other on the other, let's tile these. Well, we've got a pretty good representation of what's what. Now in some of these, I mean, we've got that nice density here, but if we look at the, say, this existing stream at the bottom, well, in this example, it has some kind of long interpolations that may not be quite as crisp as what's collected by the surveyor. So both of these, they're both high quality surfaces and they both have some pluses and minuses. And here it's just there's vegetation over top of, well, this creek, and when the LiDAR data is processed, we don't necessarily get ground points where we might have liked to. So both of these are pretty good surfaces. Let's kind of jump out of here, and we're going to bring in, well, Aaron introduced it, contours. And contours seem to be, suddenly fairly common, and they were then they weren't for folks defining their surface. But I'm going to bring in this contour file. And, well, just like before, we can see we've got a series of, well, in this case, they're all lines, but there's points in those lines. And we can model our surface from them. One, on the flatter areas, we've got these really long interpolations between points, so we don't have the little undulations there. And in this case, if they're longer than the maximum side length that we've set, we've got these holes in our model. Let's go down here where we've got a little bit more going on. So right off the bat, we can see it's pretty common with contours that the tops of your hills are going to be cut off where they don't have another point to jump up to that next contour and round things out. Similarly, on the ridges, we've got these little flat spots coming down the ridges. And then we've got these flat spots in the valley bottoms as well. And of course, well, if you're using our software, there's a good chance you're doing some kind of corridor modeling. And well, contours, they're defining between elevations, and we obfuscate where other features may be, like existing roads and what have you. So not ideal, and it really is just that. It's not ideal. If it's the only thing you have, or it's the best source of data that you have, well, it's certainly better than nothing. But if you have access to, as Aaron said, the raw survey data, whatever format was used to define these contours, it's usually a better bet. And it doesn't have to be just the original data. So in this particular example, the original data is my last data, but I could also get by pretty easily using a high quality DEM surface. So here it's going to be a derivative of the tin that we created from our last file, or someone created from the last file. And we can bring that in and we can see, well, same idea, lots of points. We're going to calculate that surface. And it looks pretty similar, just given how, well, how dense the data is. It looks pretty similar to our LiDAR. And DEM data is really nice. It's a really compact format to transfer data. It reads in very quickly. And oftentimes we end up using it interchangeably with the LiDAR itself, provided that it's high enough resolution. Now, what if we had this at a much lower resolution? So we could bring in another example, and I'm not going to bring in the data from scratch. I have another example set up here where it's already done, but I've got low resolution, high quality data. So it's the same, comes from the same surface that we started with, that last data, but instead of having a 1 meter point spacing, we have a 30 meter point spacing. So we can see that they're not quite the same, and I'm going to turn off that yellow surface, which is our high res surface. And we can see, okay, that's what we're actually dealing with that 30 meter resolution. Now, it's not just resolution that influences the quality of the surface that you're working with. And we could come in here and we could grab, well, this is a low quality or low resolution surface. I'm going to make this one, I will make it cyan. So here, going from that gray surface to this one here, well, it's quite different. So in terms of, as we get into the design space or calculating volumes, well, if we're comparing two surfaces and one of those surfaces doesn't represent the ground that we're actually well, intending to design on, well, we're going to introduce a fair bit of uncertainty in what we're working with. Again, not the end of the world if it's the best you have, or maybe you're doing something really preliminary and you don't have a need or can't justify the expense of getting higher resolution data or higher quality data yet. But certainly don't go into it using really poor quality data and expect to get the same results as if you're using high quality data. And with that, I will pass it back to Erin and we'll continue along.
Okay. Thanks, Matt. Next topic we're going to lean into is really understanding a bit more about the cross-section based model that really forms the foundation for our alignment design. And of course, that cross-sections model and its interactions with the centerline as well as the TIM. So to kind of explain this, we've got a couple of graphics. So of course, we start with that tin surface. We just took a look understanding a little bit more about those tin surfaces, their quality and accuracy, etc. But now for this, we're going to move more into that alignment side. So tin surface, got an alignment. That alignment is represented by a center line. And really attached to that center line is what we call a cross-section template. Now, cross-section templates are basically like little mini programs that can define the road widths, its slopes, et cetera, et cetera. And you can, of course, have multiple different templates that get assigned to different station ranges. But let's just take, for example, this project here. We are going to be looking at and thinking about that cross-section anywhere we have a report point. And I know report points is the next topic after this. So we're going to go into that in a little bit more detail there. But here, they're represented by these purple spherical symbols. So these are denoting the locations where that cross-section that I had up on the screen is being calculated. And that's really feeding the designed surface of your road. So, you know, we take that cross-section, apply it to that center line, calculate it at the report points, and that's what we have here on the screen. So if we go a little bit deeper into this, cross sections are essentially mini programs. And we've got a lot of different resources available that talk about how to work with them. And we probably could fill, you know, 2 webinars of content with it, which we did. So those are some of the resources. We can certainly share those out in the video link as well as in the e-blast that comes out after this webinar. But these mini programs get calculated at those report points, and you have an ability as well to work with multiple cross-section templates. And you might wonder, you know, how do you transition between 2 different cross-section templates? And I wanted to very quickly introduce the idea of taper templates. So again, tin surface, center line, mini cross-section program that's going to adjust and define that geometry depending on the conditions, whether you're in cut or fill. And then we have this really cool idea that you could say take a template. So call that template number 1, certain width, template number 2, a different width. And there's ways that we can set up taper templates or overrides to be able to transition between 2 different templates. And this is really, you know, important from a geometry standpoint, because then you're not having that abrupt, you know, 10-meter wide road going down to 5 abruptly. You can transition over a defined station range. So I feel like that was a terrible introduction. Let's go into the software, take a look at a little bit more about our cross-section and centerline based model. So Matt, it's coming back to you.
Okay, so not starting from scratch here, we have a design that, well, it's already a lot of work has been done. We've got an alignment. We can see, well, we've got geometry here, geometry there. Things change. I'm going to just get out of the 3D view here, and we're going to take a look at what we actually have going on. So at this particular location, I can see I've got this rock fill extending down. And then if I come back here, I'll choose somewhere that's a little more interesting than that. This one doesn't have rock fill. So how is that defined? Well, we have assign by range, and I can see, well, on my templates tab, I can see I've got the default resource low volume road applied from the start to station 67. And then I've got that rock fill applied from station 67 to 95. Now those templates that I have to pull from that I can assign based off station range, we can see them in the drop-down list. Or I could pop up into the template editor, and this is really the collection of templates that we have that appear in this drop-down list. So for this, if I come up here, we can see, okay, that's what that one looks like. This is what, well, just a basic machine trail looks like. And there's that rock fill that I was looking at previously. Now, with these, if we're in kind of our model side of things and we wanted to mess around with things, well, right here, we can see there is a ditch. There's a little bit of a fill slope. But if we pulled this way over here, oh, that changes. So it is dynamic. It's dynamic, and we can see right now, we no longer have that ditch on the inside. I'm going to hit undo because that's obviously a pretty lousy spot to put a road. But if we wanted to have something that's different than those templates that I introduced, and maybe we've got a little bit of variability in this resource road that we're looking at, but maybe from say here to there, I wanted to go with a wider road. Well, if I were to apply that, well, one, I'd check the station, and here, usually I have that at minus 586, and I'll go up to here and we'll assign that to minus 28. I'd come in here and I'd say, well, I've got this resource low volume road. I probably want this wide road to be very similar to that, just a different road width. So I'd take this, I'd copy it, I'd hit paste, and in practice, I'd change the name to something easy to remember. But here I'm going to just change it to, instead of being a 6 meter wide road, I'm going to shoot for 10. So 5 meters either side. I'm going to come in here. I'm going to apply that new template. And so we're going to choose that template that is called XX0. And we're going to go from that minus 58.6 to minus 28. We'll hit add edit. We'll hit OK. We'll let this thing recalculate. And well, it might not be obvious to folks looking from that perspective, but if we zoom in, we can see, well, now we've got this really abrupt transition, and we'll come in here a little bit further. And yeah, we can see that we go right from, well, I'll go back one. We've got 30, we've got 28, 1, and 28. So unless we assign it, there's going to be a transition length between our templates of 0.1 project units. Now, and here I'm working with a metric project. So meters, if you're working with an imperial project, that would be 0.1 of a foot. If instead I wanted this to, well, go from say 28 meters back to that narrower width, I could come in here and I could say, well, let's go from station minus 28 to 0. We're going to apply this TP template. So in this list, we have 2 templates that don't appear in the library, but they always appear in that list, and that is the BR, and it's just a bridge, so no cut, no fill. And then there is the taper, and that just looks at the template assigned before and the template assigned next and transitions from one to the other. So we'll hit that here, we'll hit OK, we'll hit OK, and voila. Now, the other thing we could have done there is, and where should we do this? Let's do it back here. If it was something where we maybe just wanted to change one template parameter. So in this previous example, we changed the width, well, maybe I don't want to have a new template in my list. If I wanted to do something like just apply a widening, I could go in here, and instead of messing around with my templates, I could go to my overrides and I could say, well, let's widen the parameter called width. We're going to start our transition at minus 700. And here I'll mention it after. Usually I don't start my roads with a negative start station, but I did here. And so from station minus 700 to minus 680, I want to go from that default width to have a width on the right side of 10 meters. And then I want to carry that 10 meter widening ahead to, and maybe I'll carry it 30 additional meters here. And then we'll taper back in by, we'll taper back into our default here. So we'll hit OK, we'll hit OK, we'll hit OK. And we can see that widening is applied. And the nice thing about doing that with our overrides, instead of having to, well, it is nice to not have to make an extra template in your library of templates. But the other benefit here is if we decide that we want to keep this assignment range kind of relative to itself, but maybe we want to move this ahead, well, we could just select all 4 of these assignments and we could say, well, let's move that up to station minus 650. We can hit OK, and we can hit OK. And we see it gets moved ahead. So it's nice that way, and we can duplicate it, move it around however we'd like. So yeah, with that, templates, they're, as Aaron said, like little mini programs with a bunch of logic in there that we can use to, well, account for whether a ditch should be assigned. I won't get into here because, well, we've only got so much time, but we can cover all sorts of different things like walls and berms and benching, etc., in terms of logic for when they get applied and when they don't. And of course, those cross-section templates are attached to our centerline. So as we move our centerline around, well, the cross-section geometry updates relative to the topo surface and the centerline position to give us these really nice and dynamic 3D models. And with that, I'll pass it back to Aaron.
Okay, probably the most important topic of the whole presentation, and probably one of the most misunderstood concepts as well. We touched on them ever so briefly. They were those little purple spherical symbols that we had attached to our centerline, and those are report points. So report points are basically cross-section calculation points. And they really do help us to make sure that we get reasonable volumes and a reasonable representation of our site geometry. Now, they come in a bunch of different categories. For example, when you go and design a road, there is an auto interval point. These ones are used throughout your project. They have a certain length between them, or should say distance between them, and you can configure that. When you add a curve, you get report points added for your curve geometry. When you add a culvert, you get a report point added for your culvert location. And then, of course, the final sort of major group of report points are the ones that are the standard editable report points that you add yourself. So a couple big key concepts, I should say, around report points. First of all, the more report points you have, it's going to increase your accuracy. And I think a switchback is a wonderful example for this. So here's our switchback. You can see in the 3D model here, we can actually see, we display them. All these black lines represent our report points. Now, in this particular switchback, you can see the geometry in particular around some of these sections of the curve are not being accurately modeled. There's not enough report points. So if we increase the report points, as you can see in this second image here, again, the black lines in the 3D window are showing our report points. You can see that the curve geometry is much better displayed. And switchbacks are a really prime example of this. They need a fair bit of report points enabled to be able to see them. Which then brings us to our second concept, because you might think, oh, great, more report points is better. I'm just going to add tons of them at a really, really tight spacing. Well, it does have an impact on your design's performance. So one of the biggest, most fun things about RoadEng is its speed. You're designing really quickly. Everything's updating interactively. Well, the more complexity we add to the model in terms of report points, we are going to slow calculations down. So there's lots of situations, for example, the one on the PowerPoint slide here, where too many report points is going to, first off, make it slower, and secondly, not really improve the accuracy of your design. You know, in flatter, simpler sections, you don't need as many report points. It's not going to have any meaningful difference other than adding unnecessary weight, I said that in air quotes, to your project. So with that, report points. If you're taking away anything from this webinar, hopefully this section is going to be the one. Matt, I'm going to pass it over to you for a couple examples of report points.
Perfect. So we've got another example, and this example, well, we'll have a peek at the 3D view. We can see we've got our road, comes around this kind of big sweeping switchback, and we'll zoom in here, and well, we can see that the center line is a nice smooth curve, but the other geometry is not. If we go back to the plan view and zoom in at that same location, it becomes a little bit more intuitive that, well, these locations where we've got these report points are where we're generating the cross sections. Now, I've intentionally, coming into this webinar, wanted something to talk about. So this is less dense than I'd typically use. And if we make it even less dense than this, we could come in here and we could say, well, what if we drop this back to 50? And we can see now our center line actually is on the other side of where our road edge is showing up, just because there's no report points landing in between here. So, well, where did I change that? We can change it in a few different spots, but I did it in my corridor ribbon options. And I came in here, and actually in that previous example where I had my negative start station, if I want to change my station numbering, I can do that here. But report points, we click this little button and we can see we've got a whole bunch of different classes. And if I wanted to change that auto interval report spacing, I could. And I'm going to just drop this down to 10. And I said that that 25 was less dense than what I'd normally go with. Well, it's less dense than what I'd normally go with on a project like this, where there's a fair amount of curvature that I want to account for, hence the switchback. Also some irregularities in the topo surface. But if I was dealing with like a higher speed road on flatter terrain, nice straight, well, maybe that 25-meter interval spacing that I had is appropriate. So there is a reason that we don't just set that and tell the users that that's what you have to use. It is a user-defined setting, and it influences, well, everything from just the validity of the model itself to your volumes to where your cross sections are being calculated, etc. So I'm going to crank this down to an interval of 10. We'll hit OK, we'll hit OK, we'll hit OK. And we see we've got this much nicer representation of that switchback, and away we go. Now, another example of where switchbacks come into play, or sorry, where report points come into play, is accounting for details and transitions. And well, obviously we want to account for where the topo surface is, but one that might fly under the radar a bit more is if we are using reference surfaces. I'm going to zoom in here. So different alignment in the same project. And in this particular example, it being a wind farm example, I have my pad geometry defined based off the extents of a reference feature. And that reference feature is this line available or visible here in the plan view, but I'm not catching the edges perfectly of this. Now we're dealing with a cross-section model. And if we want to get a better representation of where we should start transitioning back towards the road edge from the pad edge, well, report points will be helpful for that. And we could go in here and we could crank this down and we could say, well, 25 isn't capturing that. Maybe we want to go smaller. And if we go too small though, and if we're doing it at this level, it's going to be a global setting. So we wouldn't want to put this in at 1 meter because while it's effectively making, in terms of performance, our road 25 times longer in terms of computation time. Now, we could instead leverage another class of these report points, which is the standard editable report points. And these ones are just where the user decides, I want to tell the software to add a report point here. So for that, I could just right click. I could click Add Edit Report Point Tool, and I could come in within the location where I'd like to add it, and we can throw one in there, and then we could throw one just on the other side, and we've got a crisper connection. And we could do that wherever we'd like. Now, besides that, if we wanted to do something that was somewhere in between just assigning individual report points or assigning a global setting, well, maybe we just add a spacing in for our report points. So if I want to go from we'll go from station 4996 to the end of my road, and I want to crank up that spacing to be 2 meter intervals instead of adding them individually or adding that to the whole thing. We could come in here, auto-generate, and we could say, well, from station 4996 to the end, I want to add report points at fixed intervals. I could remove existing if there are already ones I want to remove, but we can come in here, assign that, and we'll go to the end here, and we can see we've got a much denser spacing where we've assigned that. So pretty easy to work with, super important concept. It's kind of at the heart of a cross-section model. Well, centerline is important, your cross-section geometry is important, but of course, where that cross-section geometry is being calculated is important, and hence Aaron's emphasis on, it's kind of boring report points, but it matters. So will probably help you in the future if you're trying to capture a detail that's otherwise difficult to capture. With that, I'll pass it back to Aaron.
Awesome. Okay, let's put it together. So we've talked about a tin, we've talked about our center line, our cross section, and we've talked about our report points. And together, all of those items really are the backbone of the math that is being used to calculate volumes. So again, let's advance my slide here. That cross section, it's attached to the center line. We're calculating that cross section of the different report points. And really, this is kind of the process that's happening in the background, when we look at it. So this is a basic graphic depicting what's called the average end area volume calculation. And I think it's kind of nice for folks to really understand where their volumes are coming from. So that length between report points, the further apart they are, obviously, the less accurate to your calculations are going to be. So trying to find that balance point between performance and accuracy is really important. So volume calculations, they are cross-sectional areas applied against that sort of length between the report points. And really, being able to, and I should say this is a very simplistic depiction, we are able to get this in a lot more detail, especially when we start working with multiple materials, which we'll touch on ever so briefly here in a second. So this is really important. Again, re-emphasizing that importance of report points. It also re-emphasizes, some of the engineering decisions that you, as an operator of the software, need to decide what you want to go with in terms of that spacing, in terms of the accuracy. So now that we've calculated our volumes, really the next set of core concept to help you better understand RoadEng is the mass haul. And of course, the mass haul is really just a reporting method for the volumes. It's done along the length of the road. So the bottom axis that is our chainage or our stationing. The purple line is our material balance. So in just quickly explaining this graphic here, on the left side, we start off with a cross section that is predominantly in cut. So when we're in cut, our mass haul is going to rise. As we move more to the center, you can see that we're now predominantly in fill. So when we are in fill, the mass haul is going to start to fall. And then when you have sort of a more equal or balanced cross section, the mass haul absolutely flattens. So the mass haul graphic is really useful, especially as you're designing. It helps you visualize how much material is needing to be moved, if you're in a deficit or if you're in a surplus, and really helps you just save some time, cost, and effort, especially when it comes to constructing that road in the end. So the mass haul, important concept. It leverages all those volumes we've calculated into a nice graphic format. And then finally, kind of just adding one other layer to our volume calculations. And again, we actually spend a lot of time talking about materials in other webinars. Encourage you to check them out. Different materials have pretty significant impacts on your design, whether you can use a material, whether you can't. And in what we're going to talk about today is they have a really large impact on volumes. So if you are not considering this concept as you design, we certainly encourage you to. So we like to think of materials occurring sort of in three main states. The first state that a material can be in is banked, or it says that it's in situ. So it has yet to be excavated. It's sort of its resting state. We then think about it also in its loose state. So this is that's getting transported. And then of course, once you've replaced it or embanked that material, it has another state. And each material, whether you are working with solid rock, fractured rock, gravel, clay, you name it, all of these different materials are going to behave differently in these states. And we need to be able to account for those changes in our volume, and doing so by material. And to do that, we have something called expansion and compaction factors. And here we can adjust, if a material is swelling, we can adjust its factor to account for that. Or if it's going to shrink when it's placed, we can account for that as well. And that's a really, really important concept because it's, again, we're talking about things that have a really large impact on design, quality of your tin surface, frequency of report points, as well as the behavior of the materials that is in your topo surface. So, Matt, I think we're coming back to you. Let's take a look at volume calculations and unpack a couple of those concepts.
Yeah, it's kind of all interconnected here. And I'm going to jump back and forth between two really simple examples before we look at a real example. So this example that we're looking at, it's super boring, and it's super boring intentionally. So we've got a nice planar surface, we've got a flat road, and in this particular example, we've got that center line set right on ground, and our cut is equal to our fill. So we can report that cross-sectional area, and we can see that, okay, down here we've got subgrade fill area of 10, subgrade cut area of 10. Over on the right, we can see our profile, and not very interesting since the center line's right on ground, and our mass haul is not showing anything. And that's because, well, in this case, our cut is equal to our fill, and if we were going to build this, well, we'd probably just take this material from here and put it over there. So there's no surplus showing. If we switch over to have something that's slightly more interesting, we may have something that looks like this, where, again, same example, just moved around a little bit. But we start off, we develop some cut material, so we're excavating more than we're filling. and that material comes ahead to here, and well, we zero out by the time we get to our end of our road. So cut portion, this little flat spot where we flip over, it's going to be right at 0, and then we get rid of that material as we go ahead. So pretty simple concepts. I'm going to go back to that one that balances perfectly side to side. They both balance perfectly, but one balances perfectly with no longitudinal movement. And well, if we were building this and we had something that our in situ material flopped over, we placed it, we compacted it, and it ended up being the equivalent of that, well, our expansion and compaction factor would be 1. We don't really have to worry about it then, but that's rarely the case. So if we had something where we expected our fill material to shrink, well, and we wanted to work in bank cubic meters or bank yards, we'd set our cut factor at 1 and our fill factor to be, well, another value. So if it's shrinking, it's going to be larger than 1. If it's expanding, it's going to be smaller than 1. We can hit OK. And we see we've changed some stuff. And we've changed it so that our areas are adjusted. So my cut here, my cross-sectional area is still 10 square meters. Adjusted, well, cut factor is 1, so don't have to worry about that. We come over here though, we see that the geometric area for that cross-section is 10, but then we have the adjusted area where it's saying that it's 12 square meters. And all this is doing is saying that, well, the cut equivalent to make that up is we need 12 cubic meters of cut instead of 10 cubic meters, so shrinks. Now, with that little bit of a change, we've actually had a pretty substantial impact on things. Pretty boring geometrically, since it's, well, not really a pure geometry problem anymore. It's this idea of states. And now if we know that our material is going to shrink, well, we'd actually end up, if we built this exactly as designed, we'd end up 2,000 cubic meters short instead of not having to do any longitudinal movement. Alternatively, if we had have said that, well, maybe we're dealing with rock and this material is going to expand, same but opposite, where we'd end up with too much material. And then of course, if we come back here to that, still pretty simple, but slightly more complicated, we can assign those shrink and swell factors to different materials. And in here, we've got, well, some solid rock, we've got that overburden, maybe some of our overburden is going to shrink, but the rock is going to expand, and voila, we can see that, well, it actually does change things. And of course, we can go even deeper with it as we get into the OptiHull side of things. But for now, we're going to keep it kind of at that superficial explanation. And the mass haul is often used to approximate material movement. So it comes, cut is above center line, it's getting moved ahead to that 0 line. If it's below, it's getting moved back. Let's have a peek and tie this all together at something that's a little more interesting. So this example, it was designed using the LiDAR surface that we have visible. If we wanted to see the volumes of what we're dealing with, well, we could. So we've got our data table over here, and I've got that cut volume, fill volume. We can see we're very close to balancing in this. We can keep track of our different materials. This summary is actually being summarized based off of our report points. Now here, I only want to see it every 200 meters. I don't want to see it between every individual report point. So we don't have to show every individual report point, but it's still accounting for all those points that land between, well, 0 and 200, 200 and 400, etc. Now, with this, we can step through those cross sections. We can see what we're dealing with. There's our cut volume. We've got some fill in here, and it's just an extension of all those pretty basic concepts that we've covered. And well, if we go right back to the start and relate this back to our topo surface data, this was LiDAR data. Well, what would it look like if we used that really low quality SRTM surface? And let's switch over our reference topo. We'll hit OK. And I'm going to refresh my 3D view, and we could see that, well, that difference in shape and accuracy, it adds up. So here that SRTM data actually has a bias where that surface is higher than the one we're looking at. We can see it's a lot smoother. And while our volumes skyrocket, we're meters below where we should be. And in practice, well, you wouldn't put that there. You'd have to move it up and redesign things. Now, what happens if instead of starting at that kind of high-res surface, if we started at this low-res surface and compared them? Well, we've got one here. I'm going to just make this surface so we can see it. So if we designed on that surface, and we'll make it so we can't see that other one, well, it looks pretty reasonable. But, and this is kind of that just driving it home in terms of expectation, if you designed with this, but the actual ground looked like the other, well, we should expect one, estimates to be off, and then two, we may have to adjust things for where things actually go. Now, just for context, this example designed around this surface, this low quality surface. These lower quality surfaces tend to smooth things out, and the high points tend to be shown as being lower and the low points tend to be shown as higher. Well, we're only cutting and filling 4,500 cubes. That shakes out to being 75,000 in terms of our cost model in this particular example. Apples to apples comparison, going back to the LiDAR surface and going back to surface here. Well, it's designed optimally around this better surface. We end up with 7,700 cubes. Total cost 130. So yeah, it's important to account for this stuff. And then if we compare where it makes sense to put the two roads, all else held equal, and it's kind of hard to look at it in terms of the 3D since they are so different, but all else held equal, where would these two land? Well, we've got them in the right general location where we're going across the same hill, we're going up the same draw. We're not wildly off here, but we're beyond what would be kind of easy to adjust on the fly. So I've got a difference of 45 meters there. I've got a difference of 92 meters there. So it's certainly doable. It's useful from that, okay, can we get there standpoint? But yeah, don't rely too heavily on low quality data for your final deliverable. And with that, I will pass it back to Erin, or maybe we'll dive right.
Yeah, I think we're actually, guys, gonna wrap up there. We went, surprise, surprise, a little bit over time, but I really hope that all of you kind of can get some key takeaways. you know, as we looked at some of these core concepts, whether that's in the example Matt brought at the end, fantastic example of the impact that your topo and your TIN model have on your ability to design. We talked a lot about report points. We talked about the volume calculations, and in particular, looking at things like your, you know, the frequency of those report points, your expansion and compaction factors. We really hope that you guys can take some of this away, think about it, you know, as you're doing your projects in the software, as you're making some of those engineering decisions. These are really, yeah, foundational items that we hope you now have a much more solid understanding. Thanks for hanging out with us a little bit over time, and we look forward to seeing you all at another upcoming webinar soon. Thanks, Matt, and have a great day, everybody.
Thanks, everyone.